Hi there, I welcome you to my YouTube channel. In this video, I'll be describing and explaining the oscillations of a mass spring system. And in my previous videos, I've taken time to explain oscillations, simple harmonic motion, the basics of it, and even deriving the period of a simple pendulum. So in this video, I'll describe the motion of this mass spring system and also go ahead to derive the expression, the equation for the period of a mass spring system. So here you are given a system of a mass spring system. First of all, you have a mass in this first diagram suspended below this point P. And then the L naught here is the natural length of the spring, the unstretched length, unextended length. Because you can see that at this point there's no mass yet attached to the spring. Okay. Now in the second picture, you can see that a mass M is then attached to this end of the spring, and that mass stretched the spring by E. E is the extension produced by the weight of this load, of this mass that is attached to the end of this spring. Okay, and in the third diagram or picture, you can see that this mass, the mass spring system, is pulled down by a total force F, and then before it is set into oscillation. Okay, let me come back here. In the second diagram here, we are still looking at a case where the system is in equilibrium. That is, the mass spring system is not yet set oscillating. And then, of course, the weight of this mass is given by m times acceleration into gravity g. That's the weight. That's the downward force acting on the mass. And for this to be in equilibrium, of course, you know from the principle of equilibrium that at least two forces must act on a system that's in a state of equilibrium, which means this weight of m will be balanced by another force. That force is called the spring force. Okay, and then this spring force must act in the upward direction. Okay, let me call the spring force Fs. Okay, now since it's equilibrium, and again I take this line as my reference line, it's going to be the center of oscillation when we eventually set this mass spring system oscillating. Okay, so it means that since the system is equilibrium, the spring force Fs is equal to the weight of the mass mg. And from Hooke's law, we know that when a load is attached to a string and then such that it stretches the spring, now the spring force is equal to the spring constant multiplied by the extension. This is the equation that relates the spring force and the extension produced by the load mg. Okay, so I'll call this equation 1, or I can write mg is equal to spring constant times E. Of course, you know that spring constant K is what determines the stiffness of a spring. If a spring is highly elastic, it has a low value of K. If it is very stiff, then it has a high value of K, and is defined by the force applied or the load over the extension produced by the load F or Fs. All right, so let's move to the third picture. You can see here that the total force, this force is applied to move this mass downwards, and before it is released, the total force acting downwards is now F, which also includes mg. Now, before we set this oscillating, we have what we call the restoring force, the spring force again, that tries to restore this mass spring system to the state of equilibrium. Okay, so and it acts upward. So the restoring force F, maybe I should call that the restoring force F. I may use a symbol F for my restoring force. Restoring force, acts in the upward direction. And the only force acting downwards is the weight mg of the mass spring system or the mass. Okay, so you know that we apply this force to pull this mass spring system downwards. That force that is used to bring this mass downwards is balanced by the restoring force, by the spring force, which acts to bring up, to restore the mass spring system to the state of equilibrium. So that's why the direction is upward and not downwards. So the only force acting downwards is the weight of this mass m. Okay, so which means I'm going to write it down this way that the restoring force F using the Hooke's law equation is K times the total extension, which is Y. Because since mg initially stretched the spring by E, and then by pulling this, applying some extra force to pull it down again, the total stretched length of this spring is now Y. That is, it's stretched from this level, because here before, up to this level down here. So the total extension produced by force F, which is balanced by the restoring force, is equal to E plus x, and that's my total extension y. Okay, so I can still write this as k into e plus x. Okay, so I can call this equation 2, so to speak. Now, we want to look at, since there are two forces acting, this is expression for my force F, and I also have the weight acting downwards, two forces. Before we set this mass spring system oscillating, we know that we need to find the resultant of these two forces. So we can write the resultant restoring force. The resultant restoring force now is now the difference between the spring force. I can take the downward direction as negative and the upward as positive. Okay, so I can say this is F, which is the resultant force. Let me call that FR is equal to mg minus F. This time around, I'm taking the downward as positive and the upward as negative. You can equally reverse the direction. So we have, since the resultant force is upward, I think it's better we take the resultant force, upward direction as positive and downward as negative, because the resultant force will be upward since this force F is greater than mg. All right, so I have minus mg plus, what is my F again? I can bring in my k into e plus x. Okay, I hope you are following. So that is minus mg plus ke plus kx. And from Newton's second law of motion, we always express resultant force as equal to mass times acceleration a. Okay. Now come back to equation 1, where we have mg equals ke. Can I replace this with my ke? Since mg is equal to ke, of course, we can go with that. So minus ke plus ke plus kx is equal to mass times acceleration, because I think I can move to this side because I have enough space here. So we have this cancels out, this gone. We don't have any need of this. You can get rid of it. So that gives us kx is equal to me. All right. Okay, so in terms of magnitude, let's just work with magnitude, because sometimes the way you subtract the two of them, the answer will be negative. Okay, so which means the acceleration of this mass spring system is given by kx over m. And then if you compare this with simple harmonic motion acceleration, A is equal to omega squared x. Notice that this my omega squared. If you compare these two equations, omega squared is my what? Is my k over m. Omega squared is my k over m. Where is it again? Okay, that is it. So from that I have omega squared is k over m, and then omega is what? The square root of k divided by m. So that gives you the equation, the formula for the angular velocity, angular frequency of oscillation of a mass spring system. Either you say omega square is this, omega square is omega is the square root of spring constant over the mass on the spring, not mass of spring. This is mass that is attached to the spring. All right. Okay, we can proceed to derive an expression for the period of this body now. Let me move to another space where I have enough space. Okay, bear with me. I have to use this to do my analysis. Okay, we are trying to find a period. Now, for the period of oscillation of this mass spring system. Now, when I release this mass, in this state, in this position, it goes up. Since it's pulled down by distance x, what it means is that this x becomes the amplitude of oscillation because it's going to rise above this reference line by another distance x or x naught, and it's going to be swinging, between in the vertical plane between this line or center. We also call it the center of oscillation. So it goes up and down about that line. All right. So to determine an expression for the period, we come back to the equation for the angular frequency, which gives us the square root of k divided by m. All right. So um, we have this is 2 pi over t. Of course, I've already shown that the angular velocity or frequency is equal to 2 pi over the period or time period of oscillation. That gives me square root of k over m. So that if I rearrange this now, take this up and bring this down, if I swap the two terms there, I want to also swap these two. I take m up and I bring k down. So that if I cross multiply, I have the time period is 2 pi square root m over k. So that gives the expression for the period of this body in simple harmonic motion. I guess you can derive it. All right, so in the next video, we'll be solving some questions with this.